Representation is the word mathematicians use for an action of some structure on an object. In particular, a linear representation of a group is a vector space along with a group action, meaning each group element becomes a linear transformation of the space in such a way that multiplying two group elements is the same as composing the transformations they correspond to. In this video, I want to answer the question, who cares about representation theory? Why do we care about representations? It looks like we're adding new structures to groups, and then just studying those structures because we can. All of the results I've seen from representation theory are only useful for doing more representation theory. How does this actually help us understand groups? One very good answer to this question is Coxeter groups. Coxeter groups are a clear example where representation theory makes the study of groups significantly more elegant. And the representation theory of Coxeter groups also answers another question, which, after talking about my research to some friends who weren't mathematicians, I realized is a question that a lot of people have. What do mathematicians mean when they say the words beautiful or elegant? We often use these words to explain why certain results or proofs are better than others, but it's not a good explanation if we don't make it clear what this means. This video is the second in a two-part series about the classification of finite Coxeter systems. Last time we sketchily completed the entire classification just by analysing Coxeter groups directly, and my hope is that by the end of this video you'll understand why we consider that method to be inelegant, and the method in this video to be elegant. Of course, that's a massive oversimplification, the combinatorics is still important, but we'll get to that later. This video requires some background on linear algebra. Specifically, it would be good to know about bases of vector spaces, dot products, linear transformations, matrices, and determinants. Let's first recap a couple of things from the previous video. A Coxeter system is a particular kind of presentation of a group, which is good at describing symmetry groups generated by reflections. An element of a Coxeter system is an equivalence class of words under a set of relations which include nil moves, that double letters cancel, and braid moves, the lengths of which determine the Coxeter system. Throughout that video, I repeatedly used two examples, A2 and B3, the symmetry groups of a triangle and a cube, and I'm going to use those again in this video. What I want to do is give a more concrete description of how these geometric groups work, so that we can get a better understanding of how to take a Coxeter system and turn it into a reflection group. First, let's understand what a reflection is. A reflection is a transformation which flips a vector space around a plane, and whenever I say plane in this video, I mean something with one dimension less than the vector space. So, in 2 dimensions, you can reflect about a one-dimensional line, in 3 dimensions, you reflect about a 2-dimensional plane, in 4 dimensions, you reflect about a 3-dimensional subspace, and so on. We're also going to assume that the plane passes through the 0 point of the space, otherwise the reflection isn't a linear transformation because it sends 0 somewhere else. Let's just stick to 2 dimensions so we can draw things. Here is a plane that we want to reflect about, and here is a unit normal vector to that plane, which means this vector has length 1 and is perpendicular to the plane. This vector is called a root of the reflection, and I'm going to label it with the letter alpha. Let's now pick a vector v and apply the reflection, which I'm going to call s. What vector do we end up with? Well, we start with v, and then add on this vector, which passes perpendicularly through the plane. The length of this vector is equal to twice the length of the projection of v onto alpha. But since alpha has length 1, this length is just the dot product of alpha and v. So we have to take v and add on a vector with magnitude 2 alpha dot v and direction negative alpha. That is our reflection function. Now let's go back to the triangle group we saw in the previous video and write out these reflection functions. Here's the 2 planes for the generating reflections s and t, and here's the 2 roots, the normal vectors to those planes, which I'm going to call alpha and beta respectively. Just an aside, we could have picked this vector for beta instead, but it turns out that the maths later on is a lot cleaner if you require all the roots to be pointing away from each other. For now, just think of this as an arbitrary choice. Here are our reflection functions, and if you want you can write out the coordinates of alpha and beta in order to figure out these reflections exactly and write them as matrices. With that, we have constructed a representation of the Coxeter group A2. Now that we've turned each generator into a matrix, we can get all the other group elements by matrix multiplication. To check that this actually works, you can verify that these matrices satisfy the relations of the Coxeter group. That is, t squared and s squared are both the identity matrix, and sts and tst are the same. This already gives a simple philosophical answer to that first question we had. Most of the time, when you picture a group, you're actually thinking of a representation. We think of A2, for example, as the symmetries of a triangle, but those symmetries are actually linear transformations of 2D space. Even if we're looking at something like a group of permutations, we can treat those as permutations of the basis vectors of a vector space, which then extend to linear transformations. Representations are the natural way that we like to visualize groups. Of course, that's not all. I promised that the study of representations would actually help us practically to complete the classification of finite Coxeter systems, and we'll get to that. But first we need to take this process that we applied to A2 and generalize it to all other Coxeter systems. The problem with this representation of A2 is that we don't know the coordinates of the roots alpha and beta. Or, more correctly, we do know the coordinates, but only because we already know that A2 is represented by a triangle, so we can deduce alpha and beta have to be 120 degrees apart, and this is kind of cheating. For other Coxeter systems, we don't know in advance what shape represents them, and even if we did, figuring out the coordinates might still be quite difficult. So what I'm going to do is write these reflection functions in terms of their action on the roots. Plugging in alpha and beta into S and T gives these formulas. The reason I'm doing this is because these roots are a basis for the two-dimensional vector space, and if you describe the action of a linear transformation on a basis, then that uniquely determines what the transformation does on every other vector in the space. We could simplify these diagonal terms to get S alpha equals minus alpha, but I'm going to leave them as is for now, because we can extend this pattern to higher dimensions. Recall that the system B3 was the symmetry group of a cube, and the generators A, B, and C correspond to these three reflections. Here are the three roots for those reflections, which I'll call alpha, beta, and gamma. By the same reasoning as for the triangle, the action of the reflection functions on the roots are given by these 9 formulas. Can you see a pattern emerging? More generally, if the generators of a Coxeter system are S1 through Sn, and the corresponding roots are alpha 1 through alpha n, then the action of a generator Si on a root alpha j is alpha j minus 2 alpha I dot alpha j alpha I. At this point, it looks like we've found a representation for every Coxeter system. Just define a vector space spanned by the basis vectors alpha 1 through alpha n, and then these functions tell you the reflections. There's just one problem: the dot product. Finding the dot product of two vectors depends crucially on knowing the components of those vectors, and remember, we don't know the coordinates of the roots. So how do we find these numbers? Well, hopefully you remember from your studies of linear algebra that the dot product of two vectors is equal to the product of the lengths of the vectors times the cosine of the angle between them. We're assuming the roots have length 1, so we just need these angles between the roots, which I'm calling theta. And this is where we're going to pull in something from the previous video. Remember when I was talking about the I-type systems, the dihedral groups, I explained why a braid move of length m gives the symmetries of an m-sided polygon. It was because if you apply a reflection through a vertex, and then a reflection through the middle of an adjacent edge, you get a rotation by one side. So repeating this m times gets you back to where you started, and we saw that this is equivalent to the braid relation. But we can easily find the angle between the reflection planes as well. Let me just get a bigger pentagon. There we go. The angle in this segment is a full revolution divided by m, because the polygon has m sides. And so the angle between the reflection planes is just this divided by 2. A full revolution is 2 pi, so that means the angle between two reflections with a braid relation of length m must be pi divided by m. This also works in higher dimensions, so even if the reflections are part of a larger Coxeter system, we still get the same result, an angle of pi over m. Since the angle between two reflection planes is the same as the angle between their corresponding roots, we can just plug that straight into our formulas. Actually, not quite yet. We've found the acute angle between the planes, but there's an obtuse angle as well. And remember a while ago I said that for unspoken reasons we were choosing the roots to be pointing away from each other, so we actually want the obtuse angle, pi minus pi over m. We can get rid of that extra pi though by putting a negative sign in front of the cosine function, and now I can finally reveal why we've been choosing roots to be pointing away from each other. Remember in the last video I mentioned that the nil moves and braid moves can all be wrapped up into a single formula, as long as you define the braid lengths m to be 1 when the two generators are the same. Well, negative cosine of pi over 1 is positive 1, which is the dot product of a root with itself. That means we can use the same formula regardless of whether two roots are the same or different. So, plugging this into our formula, we get this equation. which works for any pair of roots. This gives us all the information we need to describe this representation. The action of each reflection function on each root is defined entirely in terms of the information in the Coxeter system, and then if we consider the vector space whose basis vectors are these roots, these reflection functions extend to linear transformations on that vector space. That's it! We have a linear representation of every single Coxeter system. Although there's one big caveat I need to bring up. We haven't shown that this representation is faithful, meaning that every group element gets mapped to a different linear transformation. If two group elements give the same transformation, then that's a problem, because it potentially means that an infinite Coxeter system could get accidentally reduced down to a finite system when we plug it into the formulas. It is possible to prove that this representation is always faithful, and I don't want to go over all the details because it's a little fiddly, so I'm just going to give a brief overview of the proof in section 5.4 of the textbook Reflection Groups and Coxeter Groups by Humphreys. First, take the roots and apply every single group element to them. This gives a set of vectors called a root system. Okay, caveat number one, the words root system in a lot of mathematics literature refer to something slightly different from this, where the roots need to have specific lengths. So just note that this is not quite the same, since all the roots have length 1. Lie theorists, please don't shout at me. Now, because the roots we started with form a basis for the vector space, every root in this root system can be written as a unique linear combination of the starting roots. If the coefficients in this linear combination are all positive, that is, if the root lies within the big cone spanned by the starting roots, then we call it a positive root, and otherwise it's a negative root. It turns out that the combinatorics of this root system lines up with the combinatorics of the Coxeter group in a nice way. If I take an element w in a Coxeter group, written as some word that can't be reduced, and multiply it by a generator s, there's two things that can happen. Either we get another reduced word and the length increases, or we can apply some braid moves and then cancel two generators and the length decreases. With a bit of effort, it's possible to prove that if s increases the length of w, then applying the linear transformation corresponding to w to the starting root corresponding to s always gives a positive root. And if multiplying by s decreases the length of w, then w sends the root corresponding to s to a negative root. As an example, here's the root system for A2, and recall that the group element st corresponds to a rotation by 120 degrees clockwise? Or is it counterclockwise? Okay, caveat number 2. I realize now that in the previous video I was reading off the reflections left to right, so s followed by t, but in the literature it's actually more common to go right to left, because that's the direction in which you evaluate functions. I mean, it doesn't matter as long as you're consistent, but Humphreys goes right to left, so I will too. That means st is a counterclockwise rotation. Okay, if we apply st to alpha, the root corresponding to s, we get the positive root beta. If instead we apply st to beta, the root corresponding to t, we get the negative root, minus alpha minus beta. That lines up with the Coxeter system, because multiplying st by s gives the longer word sts, while multiplying by t allows us to cancel and get a shorter word. Everything works out. Now to prove faithfulness. This is actually a good exercise if you know a little bit of group theory. See if you can prove using this theorem that any two distinct Coxeter group elements must map to distinct linear transformations. Suppose we have two group elements u and v which get mapped to the same linear transformation. That means if we take u and multiply it by the group inverse of v, the result gets mapped to the identity transformation. Now, the identity transformation is very special. It sends all of the starting roots to themselves, which in particular are positive roots. So using this theorem that I've just described, this product, uv inverse, must increase in length if we multiply it by any generator. But there's only one reduced word with that property, the empty word. Every other word can be shortened by multiplying by the rightmost generator. That means u times v inverse is the group identity, which means u equals v. So if two elements get mapped to the same linear transformation, they must be the same element, proving faithfulness. We now have a faithful linear representation of every Coxeter system. Okay, something interesting to note here. We used a lot of geometry to construct this representation, but the whole point is that we don't need the geometry. We simply construct a vector space whose dimension is the same as the number of generators, and then define an action of the Coxeter group on that space via this formula. Furthermore, you don't need any geometry to prove that this representation is valid. I've put some details on screen if you want to check that yourself. That means this process also works for infinite Coxeter systems. That's weird. What does this representation look like for an infinite system? Well, let's just pick an example and try it out. We saw in the last video that this Coxeter system was infinite. What is its geometric representation? Let's call the generators S, T, and U, which means we have these braid relations. Let's denote the roots alpha, beta, and gamma. We can write out the reflection functions, but we don't quite know what this looks like yet because we don't know the coordinates of the roots. So let's figure it out using the angles between the planes. Since each pair of roots has a braid relation of length 3, we want the angle between each pair of roots to be pi minus pi over 3, or 120 degrees. That means there's only one way to arrange our roots, and that's like this. But there's a problem. The reflection planes look like this, and those reflections are actually just the symmetries of a triangle. Instead of producing the infinite group we started with, we've produced a finite subgroup which is just A2 again. But we proved that the representation was faithful, so what's going wrong? Well, notice something interesting. There's 3 roots, but they only span a 2-dimensional space. Everything we did up to this point assumed that those roots are a basis for the vector space, and in this special case, they aren't. Now we could fix this by taking one of these vectors, let's say gamma, and shifting it outside this plane. That gives us a faithful representation and everything is fixed, but now this reflection U is a bit weird. It fixes this same plane, but it sends gamma over here, which means this is actually a reflection plus a shear transformation. Now, we still have a root system. The reflections S and T give us the same root system as A2, except in 2 layers because of the root gamma. And then when we apply U, the roots get shifted up and down, producing more copies of A2 stacked vertically. As we keep applying U, then S, then T, these copies stack up infinitely. That is what we expect because this Coxeter system is infinite, and it turns out that the same faithfulness proof still applies. But we've lost nice orthogonal reflections to make this work. Essentially what we've discovered here is that abstract vector spaces don't necessarily have a notion of angles, so we can't ensure that each root vector is orthogonal to its reflection plane, because orthogonality doesn't mean anything if you don't have angles. Now you might say, but what about the dot product? Isn't the dot product related to angles? Well, yes, but the dot product isn't a function on vectors, it's a function on components of vectors, and this algebraic approach doesn't tell us what those components are. More explicitly, it doesn't tell us what basis we should be using. To illustrate what I mean by this, let's try constructing the triangle representation entirely algebraically. The generators S and T act on alpha and beta like this. But a priori, without knowing that this is supposed to give a triangle, how do we draw this? Do we take alpha and beta to be the basis vectors? Then S sends beta to here, which means its reflection plane looks like this, and T looks like this, and that's a pretty wonky equilateral triangle. So now the question is, when is it possible to find a basis in which the reflections are actually orthogonal to their root vectors? We know it's possible to do it with A2, but we also saw an example where it wasn't possible, and interestingly, that example was an infinite Coxeter system. And this is the crux of the video, because it turns out that this condition is what determines whether a Coxeter system is finite or infinite. If there exists a basis in which each reflection plane is orthogonal to its root vector, then the Coxeter system is finite. And if there isn't such a basis, then the Coxeter system is infinite. Isn't that amazing? I mean, proving it is not so amazing. In the textbook reflection groups and Coxeter groups I mentioned earlier, Humphreys essentially shoves everything into the study of topological groups. I quote, "A discrete subgroup of a compact Hausdorff group is closed, hence finite." Okay then. That's certainly interesting in its own right, but I don't want to focus on that. What I want to focus on is this intuitive idea that a Coxeter system is finite if and only if it is represented by orthogonal reflections, as opposed to general reflections, which might include a shear transformation. But Joe, you might be thinking, how does this actually help us? How are we supposed to determine when the reflections can be made orthogonal? Isn't that just as difficult a problem? No. As it turns out, it's actually a very doable problem. Before we get to that though, caveat number 3. I should deal with all of the people currently screaming the words inner product at their screen. There is actually a basis-free version of the dot product called an inner product, but there's multiple different inner products you can take, each one lining up with the dot product in some basis. So a way to rephrase this problem is to construct the bilinear form defined by all of these cosines and figure out what conditions make it an inner product. I'm not going to do this though, because even if it's technically cleaner, I want to avoid all of that obscure terminology and instead set up the problem in a way that can be solved with just a little bit of freshman linear algebra. First, let's describe what we're trying to do more concretely. We've got a collection of root vectors, and a collection of linear functions defined in terms of those vectors, and we need to find coordinates for those vectors in such a way that each of these functions becomes a reflection about a plane orthogonal to its corresponding root vector, with respect to the dot product. To figure out how to do this, we just have to go back to where we got these functions in the first place. Recall that negative cosine pi over m was supposed to be the dot product between roots. So we need to find coordinates for these roots so that these dot products line up with these cosines. That means solving this giant system of equations. This kind of looks like a matrix equation. Let me recap a little mnemonic for multiplying matrices. To multiply these two matrices, put the matrices here, and then to get each entry of the product matrix, just take the dot product of the corresponding row in the first matrix and column in the second matrix. What you end up with is a grid of dot products. But that's exactly what we've got here. So let's do that process in reverse and unpack this into two matrices. The first contains the root vectors as rows, and the second has the root vectors as columns. Let's call the column matrix A, and then the row matrix is just the transpose of A. So this left-hand matrix is just A transpose times A. Great! We also need to give this matrix of cosines a name, so I'm going to call it the Carton matrix? Okay, caveat number 4. Like root system, the words Carton matrix mean something very similar to this matrix, but also ever so slightly different. We'll get to that at the end of the video. I'll just call this matrix C. If you know Lie theory, it's basically a Carton matrix, except that it's off by a factor of 2 and the entries aren't necessarily integers. Anyway, we now have a matrix equation, and we need to find a square matrix A which solves it. This is where we can start pulling out our linear algebra toolbox. You see, linear algebra is an area of mathematics that's really big and really well studied. That means there's a lot of nice results about vector spaces and linear transformations, a massive toolbox that we can use completely for free. What's your favorite matrix fact? Is it that any real symmetric matrix can be orthogonally diagonalized? No? Did you not know about that fact? That's okay, because neither did I until I started making this video. Isn't the linear algebra toolbox great? Okay, any real symmetric matrix can be orthogonally diagonalized. What does that mean? It means that if a matrix has real number entries and is symmetric about its main diagonal, then we can write it as Q transpose DQ, where D is a diagonal matrix, meaning every term off its main diagonal is 0, and Q is a real orthogonal matrix, meaning its inverse is equal to its transpose. This is an important theorem in a large section of linear algebra called spectral theory. Why am I bringing this up? Well, the C matrix has real entries and is symmetric, because the braid relation between S and T is the same length as the braid relation between T and S. So we can write C as Q transpose DQ by this theorem. That's almost in the form that we need. Now just a small clever trick. Since D is diagonal, we can split it into square root D times square root D, where we obtain square root D by taking the square root of all the diagonal entries, and then use some nice properties of the transpose and the fact that root D is equal to its transpose to write this expression like this. And now we can see that a solution for A is just root D times Q. Hooray! But once again, something must have gone wrong, because this works even for infinite Coxeter systems, right? Where did we make a mistake? Ah, that's right, you can't always take the square root of a number. If any of the diagonal entries are negative, then this trick doesn't work. And actually, it also doesn't work if any of the entries are 0, because then root dq is no longer invertible, meaning the root vectors are no longer linearly independent and aren't a basis for the vector space. Hang on, that must be what happened in that infinite case we tried out. Let's test it. The C matrix looks like this, and I can use a computer program to orthogonally diagonalize it, and there we go, one of the diagonal entries of the D matrix is 0. Now, it probably takes a few more steps to make this rigorous, but the result is that if any of the diagonal entries of D are 0 or negative, then the Coxeter system doesn't have a representation by orthogonal reflections, and therefore must be infinite. But hold on a second. D is the diagonalization of C, so the diagonal entries of D are the eigenvalues of C. And when all the eigenvalues of a matrix are positive, we have a name for that. It's called positive definite. So what we have found is this. A Coxeter system is finite if and only if the matrix C, the matrix of negative cosines of pi over braid lengths, is positive definite. Now, I'm sure there are some people watching this video who have no knowledge of vector spaces and are simply letting the deeper mathematics wash over them, and have only kept watching this far because of a sense of duty or because they just like the sound of my voice. So for those people, let me just take a moment to explain why this result is so brilliant. Finding the eigenvalues of a matrix is not exactly easy to do by hand, but it is something that computers are really good at. Pretty much every modern computer algebra program has an inbuilt system to find the eigenvalues of a matrix. That means we have taken the problem of checking whether a Coxeter system is finite, a problem that is potentially of infinite complexity, and reduced it down to a single command in Mathematica or MATLAB. But it gets even better. There are a lot of theorems in our linear algebra toolbox that characterize when a matrix is positive definite. One of these is Sylvester's criterion, which states that an n by n Hermitian matrix, or in particular a real symmetric matrix, is positive definite if and only if the determinants of all of its principal minors are positive, the principal minors being the upper left k by k submatrices, for k less than or equal to n. Sylvester's criterion is named after James Joseph Sylvester, who is notable for having 3 first names. Let's try an example. Here's the graph for the system B3, the symmetry group of a cube. This is the matrix of braid lengths, which we call the Coxeter matrix, and to get the C matrix we just have to take minus cosine of pi over each entry. I'm also going to multiply everything by 2 to get rid of these nasty fractions. We're allowed to do this because it doesn't change whether the resulting matrix is positive definite or not. The determinant of the first principal minor is just the first entry, which is positive 2. The determinant of the second minor is the determinant of this 2 by 2 matrix, which is also positive 2. And the determinant of the whole matrix itself is positive 2 as well. Thus, by Sylvester's criterion, the C matrix for B3 is positive definite, and therefore B3 is finite. There's a pattern here, which makes a good exercise to prove. If you know about how computing determinants works, then see if you can prove that the determinant of twice the C matrix is 2 for every B-type system. Let's denote by Dn the determinant of twice the C matrix of the system Bn. We can apply a cofactor expansion along the bottom row, and then apply another cofactor expansion to reduce this second matrix. And now these matrices are just the C matrices of smaller B-type systems, so we get this recursive relation. But we already checked that D2 and D3 were both 2, and 2 times 2 minus 2 is 2, so by induction, every Dn is equal to 2. Now, the types A and D are also produced by extending a single chain of nodes, so they give exactly the same recurrence relation, but with different starting terms. The systems A1 and A2 have determinants 2 and 3 respectively, and then you can show by induction using the recurrence relation that the determinant for An is n plus 1. You can then check by the same method again that the determinant of the matrix 2C for any D-type system is always 4. Unfortunately, the I-type systems don't follow this recurrence relation, but that's okay. For these, we can just let the braid length m be arbitrary, and the determinant of the C matrix comes out to 1 minus cos squared pi over m. But since pi over m is always between 0 and pi, cos squared pi over m is always between 0 and 1. So we get a positive result no matter what, meaning the I-type systems are all finite. The only exception is m equals infinity, for which by convention we take pi over m to be 0, so 1 minus cos squared pi over m is 0, which tells us that this system is infinite. You can probably see where we're going with this. Just do everything we did in the previous video, but with a new way to prove that things are finite or infinite, rather than showing that a system corresponds to a particular shape, or finding an infinite sequence of group elements. Just compute the determinant of its C matrix, and all principal minors if you haven't found them yet. Not only does this allow us to get through the exceptional cases much faster, it also allows us to tie off a loose end. Last time, I mentioned that I wasn't able to show directly that this system was infinite. Now we can do that. The determinants for E6, E7, and E8 are 3, 2, and 1 respectively, while the determinant of the system one node longer than E8 is 0, meaning it's infinite. And that's it. Thanks to all of the setup we did, the classification has suddenly become a piece of cake. Well, okay, maybe not quite a piece of cake. There's still a couple of steps that are much easier to do by looking at the elements of a Coxeter system. Recall that any Coxeter system that contains a cycle of nodes, more than one edge label, or more than one branch, or an edge label and a branch, must be infinite. This is very easy to see from the combinatorial description, and not very easy to see in the determinant calculation. So really, we should be using a mixture of the two strategies. But I think it is still fair to say that the methods of representation theory are more elegant, and maybe now we can finally give a good explanation of what elegant means. The representation theory of Coxeter groups is elegant because it expands our understanding of how Coxeter groups work, and to give an example of how it does this, let's take a look at a particular collection of infinite Coxeter systems, which we completely glossed over in the combinatorial approach, the affine systems. Recall that for this infinite system, one of the eigenvalues was 0. This meant that we were able to find coordinates for the roots, it's just that all the roots lay in a 2D plane, and so the resulting representation wasn't faithful. We also saw that we could kind of salvage this and get a faithful representation by shifting one of the roots vertically. Let's now try a different strategy, and instead of shifting the root gamma, let's tilt the reflection plane u corresponding to gamma in the direction of gamma. This looks like we've made things worse, because now u is no longer an orthogonal reflection, and we no longer have 120-degree angles between the reflection planes. But it turns out that this is still a valid representation and respects all the braid relations. Since the root vectors are still horizontal, all of these three reflections, including u, leave the vertical coordinate of a vector unchanged. That means if we pick a vector in a horizontal plane offset from 0 and apply the reflections, it stays in that plane. So what do the reflection functions look like on this plane? They look like two-dimensional reflections, but one of them is now offset from 0, making them border an equilateral triangle. And if we start applying the reflections to this triangle, it builds out a triangular lattice. This two-dimensional representation is not a linear representation, but it is faithful. It turns out every group element is sent to a different function, and these functions include reflections, rotations, and translations. We've found a way to visualize this system that we previously discarded because it was infinite. But it gets better. We can do this process with any Coxeter system whose C-matrix has one eigenvalue 0 and all other eigenvalues positive. For example, this system also has exactly one 0 eigenvalue. If we try drawing the root system reading the angles off the braid relations, we get the system B3 plus an extra root. So take this root's corresponding reflection plane and shift it in the direction of the root. If B3 is the reflection group of a cube, this new reflection is along the face of the cube, which means this infinite Coxeter system is the reflection group of an infinite 3D tiling of cubes. So now the question is, which Coxeter systems have this property? We just need to check all the systems whose graphs are one node bigger than a finite group, and find all the ones whose C-matrix has determinant 0. These are called the affine Coxeter systems, and it turns out there's quite a few of them. We label them by their corresponding finite group with a tilde on top of the letter. So this cycle of 3 nodes would be called affine A2, and it turns out all of the A-type systems have affine variants. You might remember from earlier in the video that I2 infinity had a determinant of 0, so it's called affine A1. Affine A1 is very simple. The two generators are two reflections of one-dimensional space offset from each other. Also, remember in the last video I said that I26 was given the special name G2, and this was related to the fact that hexagons tile 2D space while larger regular polygons don't? Now I can finally explain the connection. G2 has an affine variant, and it's the symmetry group of an infinite tiling of hexagons. The reason we can't do this with septagons or octagons is because if we try adding a node to I2M, we get a system where the determinant of the C-matrix is 3 on 4 minus cos squared pi over m, and this happens to be negative whenever m is greater than 6. Recall that our construction requires taking the square root of eigenvalues, which means in this case we'll get imaginary numbers. Things only go a little bit awry when there's a zero eigenvalue, but they go completely off the rails when there's a negative one, so these affine systems are a really special case. Now, the H family doesn't have an affine version either, but the B, D, E, and F families all do. We already saw this one, the infinite lattice of cubes, which we call... okay, hang on a second. The B systems actually have two infinite families of affine versions, which we call affine type B and affine type C. That's it! There it is! The elusive C family we were looking for in the last video! The infinite lattice of squares has symmetry group affine C2, and the infinite lattice of cubes is affine C3. So what's affine B3, this thing with the branch? Well, the way I like to think of this is that there are two special shapes with the symmetry group of a cube that tile 3D space. One of them is the cube, and the other is not the octahedron like you might expect, but instead the rhombic dodecahedron. It doesn't look like it should tile 3D space until you just give it a go and see that, in fact, it does. Affine B3 is the symmetry group of this infinite tiling. And with that, we have completed the classification of irreducible finite Coxeter systems, and also extended that classification to include the affine systems. So, what have we learned from all of this? Well, we've learned that a Coxeter system is finite if and only if a particular matrix is positive definite, but in addition to that, we've learned that there can be multiple approaches to solving a problem, and each approach reveals different things about the answer. There are a lot of reasons to prefer the approach in this video over the more direct approach we took in the last video. This time, we were able to relate Coxeter systems to other areas of mathematics that we were more familiar with, giving us stronger tools to work with. This allowed us to complete the classification in a more unified way, connecting all the finite Coxeter systems with a single algorithm. But I also want to make it clear that what we did in the previous video was not nothing. In fact, it was very important for understanding the depth of the problem and the internals of specific Coxeter systems. Certain aspects of the classification, like eliminating groups of cycles or double branches, are much more straightforward when looking at the generator expressions of elements. The methods in this video weren't even entirely representation theory. We had to do a small detour into combinatorics to describe the relationship between Coxeter systems and root systems. What I'm trying to say is that even if one method is superior in scope, knowing other methods is still valuable and gives you a better understanding of the problem. Basically, knowing more is always good. Which, when I put it like that, sounds kind of obvious, but now hopefully you have a broader understanding of what knowing more entails. Now, I'd like to quickly go back to those caveats I mentioned, that the words root system and Cartan matrix mean something a bit different in the literature. You see, I've been describing root systems as something that follows on from Coxeter systems, but historically it's the other way around. Root systems predate Coxeter systems. Both of these are part of the study of Lie groups and Lie algebras, which I'm not going to explain in detail, but are fairly common in abstract algebra and have a couple of applications in physics. A Lie algebra is a vector space with an operation called a Lie bracket, and it turns out that if a Lie algebra is finite dimensional and what is called semi-simple, then its structure is entirely described by a particular collection of vectors in a particular dual vector space. That suggests that we should study these arrangements of vectors, which are called root systems. They're very similar to the root systems I've described for Coxeter groups, but with one major difference. The projection of one root onto a second root must be an integer multiple of half the second root. This is a fact you can prove from properties of Lie algebras. I mentioned earlier that the dot product isn't really universal, so for Lie algebra root systems we instead have to use a special bilinear operation called the Killing form, named after Wilhelm Killing. I'm not making that name up. The result of all of this is that these numbers in the reflection functions are always integers, and they form a matrix called the Cartan matrix, which has a very similar function to this C matrix that we've been looking at. So root systems are actually the more fundamental object, and Coxeter groups are motivated by being the symmetry groups of root systems, or Weil groups as they're often called. Although, because of the extra condition on the length of the roots, we don't find any root systems with symmetry groups H3, H4, or any I-types outside 3, 4, and 6. Also, it's possible for two different root systems to have the same symmetry group, and that's exactly what happens for types B and C. You might notice that the classification of root systems lines up suspiciously well with the classification of affine Coxeter groups, and that's not a coincidence. Each finite-dimensional Lie algebra can be extended to an affine Lie algebra, And we can also generalize even further to get a much larger family called cat-moody algebras. Man, Lie algebra theorists have some really awesome names. These are enumerated by their Cartan matrices, and the Coxeter systems underlying them are the Coxeter systems with braid lengths of 2, 3, 4, 6, or infinity, often called the crystallographic systems. Now, root systems have their own set of graphs called Dynkin diagrams, which are able to distinguish between the B and C types. Whenever there's a braid length of 4 or 6, we get two roots of different sizes, so what we do is draw a double edge for braid length 4 or a triple edge for braid length 6, and then put an arrow pointing from the longer root to the shorter one. Making a whole new system of diagrams just to distinguish cases B and C looks a bit silly, sure, but it turns out there's a lot more complexity in the root systems of affine Lie algebras, and this is where Dynkin diagrams really come into their own. Anyway, that's a long explanation for why I got so frustrated at figuring out what notation to use for this video. As you can see, this classification is important for many more things than just Coxeter systems. If you ever encounter the names Coxeter, Dynkin, Weil, Lie, Katz, Moody, Killing, or Cartan while reading about mathematics, this classification is probably somewhere nearby. It's so common that the lettering system has become embedded in a lot of other areas of representation theory. For example, you might see mathematicians referring to the so-called ADE case, where you only consider types A, D, and E, the ones that have no edge labels. These letters could be referring to Coxeter systems, or they could be referring to root systems, or root lattices, or Weil groups, Lie algebras, manifolds, varieties, or a whole variety of other things. And you better hope that all of those things are connected in the most convoluted and exception-filled ways possible, because otherwise we'd be out of a job.